Okay, and we're ready finally. Again, good afternoon, everybody. My name is Dusan Kojic, and I'm working as an assistant professor at Keio University in Tokyo. I would like to welcome you all to the conference, to Japan, to Awaji Island. I really like this place. I've been here 2 years ago, and I just love the view from the room. It's amazing. I can't pick is it the sunrise or the sunset that I like more, but it's lovely to be here again. So this is a talk that's going to take about an hour, and I'm going to be talking about Spectra of pure water. I will try to make things interesting. It's going to be a bit technical, so I hope I won't put too many of you to sleep. So the original title of the talk was to talk about preprocessing methods in NIRS. I decided to slightly change it in order to make it more appealing and more interesting. But however, I will go through preprocessing methods just for about 20 minutes talk. So, of course, why do we need preprocessing methods? Because we want to make our predictions better. And sometimes, a lot of times, near-infrared spectra. So obviously, I'm working with near-infrared spectra. I took a short look at the posters there. I've seen posters in UV, in mid-IR. I think that's about all the techniques. Is anybody using anything else? So I guess mid-infrared UV. So I'm not familiar with UV, but I understand IR, and I'm going to try to make my talk as broad as possible. I'm going to emphasize what is specific to NIR and what is not. And so near-infrared spectra are first and foremost very, very difficult to look at because they all look the same. You can have a look at a spectrum of DNA, urine, anything. As long as you're working with the liquid phase, they all look the same. So because of that, you need some ways of distinguishing between them or to make the predictions better, to make them more accurate. And that's what the preprocessing methods are designed to do. Most common, this is not an exhaustive list, but most common algorithm, and I've placed here, I also prepared a USB stick where if anybody is interested in the presentation or in any of these references, I already have them in a folder I brought here to share them. So of course take pictures if you want, but I'm just saying you don't have to, it's already there. And the presentation's you can open it in your browser, so you don't even need a Microsoft for this. So anyway, so I'm here showing basic, most common algorithms and some of the references that I have chosen to include here. This is a very good overview paper, and its title, as you can see, is dealing with the reviews of the most common preprocessing techniques. But apart from that, some of the most common preprocessing methods are normalization, derivatization, baseline correction, and temperature correction. A lot of my talk will focus on temperature correction because I believe that we have a pretty good answer for this really, really big problem in near-infrared and other vibrational spectroscopy techniques. Normalization is basically a way to scale and to make the spectra with the mean of 0 and in most cases mean of 0 and the value of standard deviation of unity. Derivatization are doing with the derivatives, obviously, first and second. When there is a good, almost everything is known about geometric interpretation of derivatives, so we know what you do, we know what they're capable of, and we also know what the problems with derivatives are. Baseline correction are meant to, so these, especially baseline correction, apply to many different techniques, mass spectrometry, NMR, not so much NMR, but mass spectrometry, Raman, and they're very widespread, and a lot of work has been done on that issue. And temperature correction is, we all know how sensitive NIR is to temperature correction, to temperature influences, so I will be paying attention to that. So without further ado, normalization, two most interesting techniques most widely used are multiplicative scatter correction or extended multiplicative scatter correction. I have personally used this a lot, and then Harold Martins has wrote an extensive library, MATLAB library, that you can use and download, and then a lot of work has been done there, and it's been very effective in the work with solid state samples. My experience is that EMSC doesn't differ, and a lot of people can agree with that, as far as liquid samples goes, with the moderate to low concentration, EMSC and MSC do not perform dramatically different in terms of prediction accuracy when compared to SNV. And SNV is like a the most simplistic transformation that you can think of. EMSC is the method in which you can basically, in order to remove scatter, you have to have a spectra that are target spectra, and you have to have spectra that don't have scatter at all, which are modeling for zero influence. And that is by a lot of people, a crucial point of maybe weakness of this method. What to use? Usually pure water is used, but we also know that the pure water is not completely 100% free of scatter. So that is all scattering techniques heavily rely on reference spectra, and those are not easy to obtain in a theoretical manner. Another thing to go around, and another thing that is a big influence in near-infrared spectra, is the difference in the variance with respect to wavelengths. And a lot of researchers have done work and have suggested to use weighting coefficients in which you can differently scale different wavelengths, and in that way to equalize them and make the scattering correction more efficient. So these 2 points are still points of development, and that's what I want to do today. This is called a workshop, so we're not going to do a lot of work, but what I want to, practically we're going to do a little bit of mind work, and I want to emphasize points in all of these methods where development is still possible. And I believe that we still need a lot of participation in this regard, because a lot of these methods are part of some commercial software. They're far from perfect, and they're far from over and completely developed. So it is still useful to dive into this and try to change a little bit. As far as MSC, I've made the point about reference spectrum and weighting coefficients. About SNV, Massard has published a paper in which he used, traditionally SNV is used that you take a near-infrared spectrum, you calculate mean value, and you divide by standard deviation of that same spectrum. And that's the best point about SNV, that you don't need a model. You can just pre-process single spectra based on itself. That's probably the main source of its widespread use and popularity. And on the other hand, that's the most contrasting feature when compared to MSC. But mean value and standard deviation are not law in any way. So instead of using mean value, medians, interquartile range, different measures of central tendencies, statistically speaking, have been suggested. So I would like to advise you to experiment with those. Don't just use things that are in the commercial software. Try to go a little bit. And the paper from Massard, I will try to find, I think I haven't included that one, but I will make sure that you get it. And they exactly did that. They experimented, and they have shown that depending on what kind of mean value you use, you can get different results. And they have shown that those results can be better. So even in the simplest case, SNV is the simplest pre-processing technique that I know of, and even in that case, there is still a lot of room for improvement. Okay, moving on, derivatization. I will not talk too much about it. So we all know that there are basically two types of derivatives: regular, which in this case are implemented through Savitsky-Golay filters, which is just an automated way to do this, and later introduced Norris-Williams derivatives. So Norris-Williams derivatives are making use of the nature of the spectra, near-infrared, mid-infrared. These data is essentially discrete data. Absorption values are continuous, and you can have any number possible in the measurement range of the instrument for the absorption value. But for the wavelengths, you will always have discrete values. And Norris-Williams are paying attention to that. Derivatives are paying attention to that, and they're changing the step and the gap between the wavelengths that are used in derivatization. And that's the main thing. However, all these, both Savitsky-Golay precisely has been the method itself. So with Savitsky-Golay filters, we can do smoothing as well as derivatization. And a nice paper that I have included is the 3 points that you can see here are the main points of concern. And what I want to emphasize, they're also the main points of development in using these methods, and that you can read them. I don't want to read this. I will leave it to you. But these are points that are showing us that it's not, we just make a couple of clicks in commercial software and boom, derivative goes out. But things are not that simple. The most common implementation of these tools are just a selection, not the perfect one, not the only one. The selection of parameters from Savitsky-Golay techniques that are easy to implement. There are many others, and another paper that is included has shown that there are ways to get around this and to make even better derivatives and smoothing transforms that better fit the data. So again, a lot of room for improvement. Baseline. This is a picture that's been taken from the paper that I have cited here. Okay, so this is Leland. They're talking about optimal choice of baseline correction for multivariate calibration. These blurred letters are trying to emphasize that there is not, mathematically at least, there is not a real difference because you use the same tool, Savitsky-Golay. You can smooth the spectra using Savitsky-Golay, using Fourier transform, using wavelet transform. There are so many methods there, and apart from a few parameters that can be easily changed, there is no difference in the math when you're doing smoothing or normalization, baselining, or even derivatives. So that's all the same mathematical calculations. So there is not really essentially a big difference between these transfers that we on surface observe as different. And this is an example. This is a spectrum of a mass spectrometer that has been this is the raw spectrum, and these are several methods that have been, this is the original spectrum, this is alternating least squares, peak detection algorithm, wavelet transform, and polynomial fitting. And this is the upward triangle. The results of all these techniques have been compared here in removing baseline. And apart from this, I've had most experience with wavelets, and I can assure you that using wavelets, you can get any of these results. And I think that goes for other, especially polynomial fitting. Any of these methods can generate all of these results if you know well enough the technique and if you can manipulate the parameters right. So, of course, this is a regular paper, so they take a few methods, they compare prediction accuracy, and they proclaim the winner, which method is doing the best. Probably the one they're proposing is doing the best, but many times there is a very, very small difference, and who knows what's going to happen in a different sample. But okay, let's go along with the story, and then I just want to tell you that from experience, I'm positive that polynomial fitting and wavelet can create all of these results. So the result that you see here is not unique to that technique. So rather than piling up pre-processing techniques, it might be a better idea to take a few and just master them as the best that you can. And the results will be there for you, of course. So here we have the outcome of the pre-processing methods, and then they're compared. And I think as it usually comes, you get a graph like this. You get a number of principal components, and you get the prediction accuracy of the model and the prediction accuracy of the new samples. And you can see that's somewhere around second or third principal component, and here around fourth principal component. And so this is, the black line is data that is not processed, and all these dotted line, I'm sorry for the poor quality of the picture, but in the publication, in the PDF file that I'm supplying, you will get much better view of that. So we're just going through this very quickly. So the point is that around principal component 3, you get the lowest error, and if you can see here, all these circles, triangles, they're pretty much lumped up around the same value, so there is not a very big difference between the methods. But the point is that pre-processing does create a significant difference, so you should use it, but which one, you take your pick. You take the one that suits you the most, that's most easy to manipulate, to tweak to your need. And here is the same thing for prediction accuracy. And of course, we see here the region of overfitting. Okay, now to the main problem, temperature correction. Here, again, I'm using another paper, quantitative determination by temperature dependent near-infrared spectra. So this paper, and it's been published in Kalanta in 2010, so pretty respectable journal. This is a Chinese group. So this is at the same time the example of what to do and how not to do it. don't get me wrong, this is a very good paper. And so what they're doing, they're using water and mixtures of water with ethanol, and they're scanning the samples from 24 Celsius to 60 Celsius. And the part that I'm not extremely excited about is written here. So they're doing this in steps of 3 Celsius, and they're using the accuracy of their instrument temperature measurement is plus minus 1 Celsius. So it's like almost 1/3 of the step, which I believe, my point is that they should use much more accurate instrument. And the errors that they're reporting here in predicting the temperature of the sample, that's what the paper is all about, is about, so this is a cross-validated error, so this is a 0.1, which, okay, I'm gonna leave it to you. So, and the calibration curve looks perfect, so it's always 0.999 something. Where is that column? Yeah, it's here. R squareds are 0.999 something. So the problem with here is, okay, there is not enough tension. When you work with ethanol, ethanol is pretty stable. And even with the moderate concentration, you're not gonna get a lot of the signal may come from or be related to CH. And CH don't play too much. They don't pay too much attention to temperature. They're pretty stable. So any solution that you put ethanol in is going to be pretty temperature stable, and you're going to get a pretty good prediction. Working with pure water, however, will not give you that satisfaction, and that's what we were looking for. Anyway, a good effort, a little improvement in the instrumentation is needed, but it's definitely a step in the right direction. We need more work like this. And yeah, especially a little more. 0.1 would be a good idea. But yeah, those are, and yeah, we have heard about about temperature, and we will be hearing a lot about it. And I just want to summarize that the influence of temperature is particularly important in near infrared, but it has been noticed across a wide range of techniques. And even though that, and even the problem has been tackled with statistically, so there have been a proposal that we should span the entire space of temperature perturbations in order to, build better, more robust model that will work. However, despite all of that, we still don't have 90, I don't know about the instrument. I'm working with the Bruker's MPA, and in case of Bruker's MPA, we have a heating element, so we can heat, but we cannot cool the samples. And I don't think that there are many other manufacturers. I hope I'm wrong. I hope there's something great out there, but despite all of that relevance and awareness about temperature, we don't have instruments to properly work with temperature. We don't have instruments that can cool the sample and heat the samples and to have really accurate measurement. That's kind of confusing to me if we know that that's a problem and we're consciously not addressing it. So how are we going to solve it? I have a proposition, but that's not my point. I would really like to see better instruments, especially with respect to temperature control. Okay, now to the main point. So this is what I actually titled my presentation, Poor Man's Guide to AquaPhotomics. I want to talk in simple terms about the variability and variance in water, and how deep the rabbit hole goes. When I say rabbit hole, this is the, we've taken a lot of I've been in Japan in this lab for 7 years, and during that time we have taken, we always take, we work with water and water-based solutions, so we always, at every experiment, we take spectra of water, and so far we have accumulated about 20,000 spectra of water. And I took all around room temperature, which is about 24 to 26 degrees Celsius, and when I averaged the main peak of the first overtone, the average value of absorption is this number. So that's what I'm presenting to you, and I have put here 7 decimals, and the purpose of my talk is to talk about each one of these. And the way that I want to do that, I want to briefly talk about the classical way that we do analysis, and then I just want to get away from it. I want to present what are the principal sources of variance. Some of them we already mentioned. Which one of them are sample related and solvent related, and finally, after that, I want to touch on a very important but often neglected instrumental variation, and I will show you some results that we actually published. That is the paper that came out in 2017. I will be mostly using data from that to illustrate my point from that paper, and that's about the conclusion will be that we can model hydrogen bonding very accurately now, much better than what we would otherwise have to do with the careful temperature control. So in this sample related, I'm going to show you first that the first decimal after number 5 here, the first decimal is describing path length, concentration effects. That the second decimal is where the temperature is hiding. That's where the range of variation is with the temperatures. Hydrogen bonding is the bands, the near-infrared water absorption bands that we are actually interested in. And they're then to the second, third, and the fourth. And in order for us to really visualize and see those bands, this is how deep we have to go. This is our point. Last but not least is something that I really like lately. I have gained a lot of attention. Unfortunately, I don't have the data, but people here from UV are very, very interesting to me at the moment because I believe we can measure this. These are very, very small changes. But as I said, I don't have the data. I will just say why do I will just illustrate on certain samples why do I think that this is possible. So, okay, let's move on to the first thing. So this is the paper that we published in 2017, and this is the paper that I have supplied it in the material, and most of the pictures are there. So the first thing is concentration. So what you're looking at here are the spectra of pure water, and using MPA's fiber optics and a little bit of help with the micrometer stage, I was able to measure the pure water at different path lengths. Usually the standard path lengths are either 1 millimeter to 510, depending on the cuvette manufacturers. But here I was measuring, so this is in a millimeter, this is 600 micron, 7, 8, 9, 10. This is the standard cuvette, 1 millimeter. This is the most standard cuvette used in the paper. So 1.1, 2, 3, 4, 5. So this is the simulation of what happens when you make a water-based solution. So you put whatever you want or need or have to in water, and that molecule, that solid, displaces water. So instead of, so as the higher you go in the concentration, the less water you will have. So this is it. This is the concentration, and from 1 to up, this is dilution. So you can really see these are the absorption units. So you can easily see that, let's say we're never working with I cannot say never, but some people are working with solid sample and different, but the range of concentration in most is not too wide. And so in some reason or realistic, this is too wide, this is too unrealistic in terms of solutions. It's realistic in terms of pure water, but in terms of concentration that you can normally encounter, it's not realistic. It's over-exaggerated just for the purpose that you can easily appreciate that the first decimal is where this path length and big concentration changes are happening. Okay, temperature. So this is the figure 11 for the paper, and I redrew it here. When you take, so in this paper I was taking briefly to get you through the material and method section. So I took the spectra of amino acid glycine. I took a lot of different samples, but after the reviewers took a look, they wanted me to focus on one, so I selected glycine. And I took, the concentration was 1 molar, and then I used serial dilutions to 500 molar, 200, 100, 50, 25, 12, and 6, and 7, or something like that. So I just made more or less serial dilutions, and this is the vector that I'm showing you. So the reviewer wanted me to correct my experiments and to do more samples and more experiments, more consecutive spectra. So they wanted me to do everything in the 10 experiments. I want to see 10 samples in each experiment, and for each sample I want to see 10 consecutive spectra. So that's what I did for pure water and for each concentration of glycine. So when I took those spectra of water that I took, and when I calculated at each wavelength, and I calculated, so here in magenta you see spectrum of glycine at 1 molar. In cyan, full line, you see an example of spectrum of water. And the dotted lines are showing you the standard deviation calculated at each wavelength for all of these spectra. And you can see that the peaks, that the standard deviation has 2 peaks, one at 1412 and one at 1492. And here, these are the units of standard deviation. So standard deviation is basically a variation around mean value. So if you have a water in these solutions, that's your mean value, and the water-related near-infrared bands are what the standard deviation is telling you. So directly from this picture, you can learn that the third decimal are the bands of glycine. They go up and down depending on the concentration, but third decimal is where they are located. Okay, so this is a little bit busy slide, but it's really telling us a lot. So what I did, I took this same spectra. So I took the cyan spectra, all the spectra, so that was 1,010 experiments times 10 samples, 10 consecutive. I had 1,000 spectra of water. So the first thing I did, I mean-centered these spectra. And I wanted to understand a little bit better what is the 1412 and 1492. So to any near-infrared spectroscopies, of course, that's temperature, you know that immediately. But let's have a look at how this really happens. So here we have a 1412 and 1492. These are the mean-centered spectra. The zero is the average pure water spectrum at room temperature. And so we have spectra that have two patterns that are scaled. One is this magenta pattern, which have positive peak at 1412 and negative at 1492, and the one that is opposite to that. So we have this negative peak at 1412 and positive peak at 1492. So those are all variation around mean value. So here on these two panels on the left and right. So first of all, I want to explain what does it mean to have a positive value here, and what does it to have a negative value here, and vice versa. So in order to do that, I took these. I took especially the 1412 because it is the most strongly changing wavelength. So I looked at at this entire range. So there is 1,000 spectra here, and at each I took this range minus the plus, and I divided it into these little bins. And in each bin, each small range of absorption, I counted how many spectra are there. And this is the histogram that is showing you how much spectra do we have at each one of these lines. This looks like a continuous, but no, there is a density maximum that is positioned here. And the point is, because this is all at room temperature. So what I did, another thing that I omitted, is that I use the compartment that I have can regulate temperature. So I was fixing everything at 32 because that's the lowest temperature that I can get, that I don't overheat the samples. So this was all done at the constant more or less constant temperature. And the point is that if we have a variation around the mean, we always expect that to be like a pure Gaussian. What we see here is that this is a very asymmetric Gaussian, and that's already a red flag. So we have to understand what is really happening here. So here I took, in order to understand this histogram, I took these same spectra, except I was counting here, I did something different. So I'm looking at the absorption at 1412, but I'm taking each spectrum and I'm marking, because for every sample, I took 10 consecutive spectra. I'm marking for each spectrum what is the number of the consecutive, of that precise spectrum, which consecutive it is. So if I filter this, if I put here all the first consecutives and all the way to the 10th, we can see that this is what happened. We get this curve. And pure water is shown in cyan, and glycine is following that, just like here. Everything related to glycine is shown in magenta, and so basically glycine is following water pretty much. So we have here that the most of the later consecutives are focused around positive values, and that these negative values mostly originate from the negative position. So most of the first few consecutives are negative, and the higher we go in the consecutives, we're getting accumulation, and here we have the largest part of the later consecutives generating positive values. So what are positive and negative values? So here is the answer. Here we have a temperature perturbed water spectra. In the cyan all the way to the right are spectra taken at 4 Celsius and cold spectra, and we have 80 degrees, and we have hot spectra. So we see that as we heat the spectra, as we go from 4 to 80, the main peak of water shifts from right to the left. And this is how this same data looks here. So as we go from cold spectra to hot spectra, this negative value slowly changes to positive value. So that's the explanation here. These are cold spectra. These are the first spectra that are taken in the cuvette, and these are the last spectra. That's what this means. So cold to hot. And what happens here, this is not a big difference in temperature because I was incubating the samples at 32 Celsius, and then I was measuring them at 32 Celsius. So the only contact with the different temperatures was while I was pipetting from the jar, from the flask to the cuvette. So that's the only temperature perturbation. The rest of this, the difference, the rest of the meaning of cold to hot spectrum, due to influence of light. So the infrared source is heating the sample and it's creating these differences. And here is my point. This is the second decimal. So with first decimal, we were at the concentration change, and with the second decimal, room temperature. So these are actually not big changes. You can only imagine that with larger changes, if you're not regulating the temperature of your sample, this will blow up to higher values. But here, basically, this is the evidence. We're at the second decimal with temperature. And why is this important? I showed you this in a previous slide. If you understand that your near-infrared bands are at the third decimal, and if your temperature variation is at the second decimal, which means that your temperature variation is 10 times higher than your bands. So you're not going to be able to effectively extract them because there's a 10 times larger shift happening with temperature. So unless you deal with temperature in some way, and that's where all the pre-processing story comes in, you're not going to be able to understand where the bands come from. Are they coming from temperature or both? And this story really goes much deeper, because even with the small temperature generates spectra as much as solutes. So it will generate wavelength shifts, and it will. So this is the topic that I'm not completely yet clear. I'm not completely clear in terms of the physical origin, because they do overlap in some way. But let's go. Let's move on. There is a point at the end. So another thing that I did is I played with these consecutives again. And here I took a window. So I have 10 consecutives, and I tried to see what is basically, I'm looking at this data. So I take 3 consecutives as a moving window, and I calculate the variation for these 3. I want to see, are these consecutives next to each other? Do they have smaller variation or not? Or what's happening as we continue to take more and more consecutive spectra? So this is telling us that the variation that starts about here, as we go further into consecutives, that the spectra become closer and closer to each other, so they are more consistent. So this kind of gives an idea already that if you would take more consecutives for your pure water and for your samples, you would be able to decrease the variation, and you would somehow cancel the temperature effect. So the thing is that even as you go with 10 samples, so if you take 3 samples, if you take 10 consecutive, that basically triples the length of your experiment. So it's 3 times more work. And even if you go there, you're still at somewhere in the middle of the third decimal or in the lower range. So this variation that you managed to increase by taking more consecutive is still not a guarantee that you will visualize your bands. So now I'm coming to the point of what we did. So we decided to generate a database of spectra that I already showed you. So we generated a database of several thousand spectra between 4 and 80 degrees. So we already generated all the temperature influence that we can deal with theoretically, and we use this database to subtract the closest spectrum to the spectrum that we are measuring. And the effect of subtraction of different wavelengths is shown here. So with this animated slide here, so we're working here with the sodium chloride. Any other solution at 1 molar for this purpose is good enough. So there are 6 panels. There is this vertical. On the left vertical, what's happening is that spectrum of pure water, which is in cyan, is being scaled from its normal value to the value of the sample and below. And this is the scaling coefficient. So this is the normal room temperature. When we go to 1, this is 1.2. So this is the scaling coefficient of water. This is where pure water is. 1 is where it is untouched. And so we go from scaling from higher values to lower values. And this is the subtracted spectrum. So this is basically the magenta minus cyan. And this is what happens. So you can see that as the distance between water and sample changes, the spectral pattern changes dramatically. And so this curve is green, but in one frame, I changed the color to yellow. If you look at it, you will notice a very short yellow curve. Okay, so that was there. Yellow curve is the curve with the smallest area under the curve. What you can see here are the second derivatives. The green curve is the second derivative of this green curve, so second derivative of the different spectra. The orange curve is just the reverse operation. Here I subtracted, and then I derivatized the subtracted spectrum. In this case, I first calculated the derivatives of cyan and blue, and then I subtracted. So just a reverse order of subtraction and derivatization, but the result is pretty much the same. In this right side, what you can see, this is the wavelength of the water. This is, okay, so we're here at this is hot water, and it's slowly moving to the right, moving to cold water. So here we're observing what happens if we change the wavelength position of the water spectrum that we're subtracting. And what you can see that they are very, very different. These are very similar, except that the effect of wavelength difference is much, much stronger than, much larger in scale than, and it affects the outcome much more than the scaling. So this is both effects are important, but this is larger and this is slightly secondary. So what we did is we used these spectra to fine tune and to find the closest, the spectra with the smallest difference, with the smallest area under the curve. And in that way, we were able to basically visualize these bands. The bands that we get from the principal component analysis, we can now see them. And again, the same thing, the derivatives here. So by changing the distance between water that you're subtracting in your sample, you can dramatically improve what your spectra look like. And that's the basis of our proposal here, that we can do that. And basically, when you do such an operation, you have the difference, and you have the both spectra, the water and the raw sample spectra that you started with, so you don't lose any information. You can analyze the different spectra, you can analyze the water that you have subtracted, you can analyze all three of them. You can just concatenate them together and then put them in PCA. Okay, so now these are spectra of glycine, so I'm just giving you another example. I'm looking at here, here you see the number. This is the count of the consecutive. So here I'm illustrating the traditional way. So the traditional way of subtracting spectra, what we're taught in statistics is, okay, you take a lot of spectra of water and then you just average them. But in that way you will cancel the temperature influence. And then you take that average spectrum and subtract for everything, all the samples that you have measured. And by using that, that's the common way, and it's not been successful. And this slide is trying to explain why. So here I have taken the spectra of solution, in this case glycine. So this is 1 molar, and these are in dilution order. And here I'm averaging all the first consecutives in these 10 experiments and subtracting. And then I'm averaging all the second consecutives. And just like what happens here with these consecutives, what I showed you previously is then when you have consecutives, you're having the transition from cold to hot spectra. And here I'm showing you what is that transition from hot to cold doing to spectra. It is changing dramatically the outcome. And now I'm showing you that in this sample, how in the real situation, how the spectra look when you go from cold to hot. You're getting closer to your analyte spectrum, and then after that you're getting away from it again if you continue to subtract. So imagine working with this data. So imagine following a standard scenario where you're taking a lot of spectral water, averaging, and then subtracting. So you're going to take one average, or maybe you're going to choose a certain consecutive, or you're just going to work with all the data. Imagine having all this data overlapped together. And imagine what you will get basically for all of these concentration levels will look like this. This is the water that is colder than your sample, and this is the water that is hotter than your sample, and this is everything in between. So even taking a lot of spectra, a lot of consecutives, and working with them together will not give you, because the result will change dramatically. And you get a lot of data, but your outcome is still poor, because a lot of those data are too far from your analyte, and they're just bringing in temperature noise. So these same spectra here that you're watching them change as a consequence of the proximity to water, and you can see that they change a lot. So by the way, these few bands here are CH bands. Everything else is mostly related to water. And what happens if you take that database and you subtract the closest spectrum? What is the outcome? So this is the outcome. These are 1 molar, and this is all the way down to the 7 millimolar. These are all experiments. This is by subtracting all consecutive. So what you can see is that the spectral pattern over 10 experiments for each consecutive of the sample is consistent. It is made consistent by subtracting the appropriate water spectra. So basically your spectra, even at 7 millimolar, so even your spectra can still be consistent. That is the proposal. And you can see a lot more. You can see these bands. So because seeing is believing, in my next slide, I'm going to zoom in on this part of the spectrum. And this is actually the picture. All of these were redrawn from the paper, and then this is the one that's actually being published. So this is the result. So this is 1100 to 1360. This is the result that you get by subtracting average spectrum, and this is the result that you get by subtracting the closest spectrum. So seeing is believing, and here you can see how much more bands can you visualize. And visualizing is not just aesthetic criteria, aesthetic tendency. If you can see the spectra, you can do a lot more. You can go with the standard PCA method with your data cleared from temperature noise, or you can play, if you like, functional methods such as Gaussian fitting, and then describing those bands in terms of like the way you can describe any Gaussian distribution by the standard band width, band wavelength, and band intensity. So you get 3 times more parameters to specify your sample. So you can do that here. Now, it's hard to do it here. It's hard even to guess how many bands there are, but there's a lot of bands. Okay, technically, chemically speaking, this is still a region where CH overlaps with NH. We're talking about glycine, we're talking about amino acids, so we do have NH. But there is a lot more information if you take a little bit of care with water. Last but not least, this is the instrumentation variability. So what I'm basically showing, this is the raw near-infrared spectrum with all the assignment, and these are the background spectra. So these are the spectra taken without cuvette, without sample, just air, vapor, air that is present in the environment. So we want to know what is the variation there. And with this experiment, we also had 1,000 spectra of background. And these are the 4 regions. This is the labeled 1, 2, 3, 4. These are the typical region. This is the water vapor bands in R4 and R3. And so that's the background spectrum. This line here shows the standard deviation of those spectrums. So you just get these bands baseline and inverted, so they look like absorption bands. Basically, this whole region here is a mirror image. So you see 2 strongly absorbing regions, and also the regions that are not visible but are here. I have a next slides to show you. Did I put it? No, I didn't. It's not important. Anyway, so there are also 2 regions that are not visible, but if you zoom in and if you properly baseline them, you can see. So there are 4 regions where water absorbs, but the rest of the region is not absorbing. And when I remove these bands and recalculate standard deviation, I get this dashed line. So there is this tendency with longer wavelengths that variation, this is not the spectrum, this is variation. So there is more baseline shifting at longer wavelengths, and that trend decreases here. So there is a significant variation, but how much? How much is this? And here I've taken this box plot of each of these regions, and this is the scale 10 to the minus third. So with the smaller band, with shorter wavelengths, you don't get a lot of variation, absolutely speaking. These bands are small, but they're small compared to those bands. These bands have there are combination bands here. So relative to this absorption, this might not be negligible. But let's just appreciate what we can see here. And we see that the variation in the baseline here is about, let's say, 3 to 5, 10 to the minus 3. And I hope I'm successful at passing the message. When we talk about 10 to the minus 3, we're talking about these bands. So this is 10 to the minus 2. So this is where the bands are, 10 to the minus 3. So if this baseline is 10 to the minus 3, then it's working together with temperature variation, and it's going to completely annihilate your bands unless you do baseline correction, which of course you can. So instrumental variation is solvable, but it is there. That's the message that I want to pass. And it is in the order of magnitude that your bands are. in a, let's say, relatively diluted solution. If your solution is concentrated enough, 1 molar, then you're not going to have this problem. That's the point. You're going to start getting these problems as you go deeper in dilution in some more realistic cases. Okay, so that's the conclusion here is even baseline shifting can contribute. I'm showing the part that is related to instrument, but it is also, of course, sample related baseline shifting. But it is not something that you can just brush off and say, no, it's not important, it's too small. Okay, finally, we're gonna compare this to what is the effect of subtraction to PCA analysis. So I'm making this point using 3 rows of data. This is a PCA of raw spectra. As you know, with the PCA, the first component is always going to be your spectrum, the average spectrum of the data you're supplying. So here we have supplied raw spectra. In the second middle row, we have supplied the spectra that have been subtracted in a classical way using single average spectrum. And in the bottom row, I'm showing you the spectra that we put into PCA that we used subtracted spectra, but by optimizing the molecule, the closest molecule. So you can look at several things here. Here, this is the raw spectrum. Here, you see the spectral pattern. I'm making this parallel. With here, you get the 98.25 variation in the first component. The second one is dramatically lower. So you get very uneven distribution of variance. And what you see here, apart from this, these CH bands that you can recognize here is mostly, this is 406, mostly related to temperature. Again, second and third principal component are how many? This is 100. This is 4 orders of magnitude lower. Very uneven distribution, and there is a lot of temperature in the second. Only in the, okay, it is possible to argue that there is a water displacement. That's what my understanding is, that a lot of this is water displacement effect, and then mixed in between second and third are temperature and wavelength shifting. And at the last, fourth principal component, you're starting to get something that looks like a band, that looks like hydrogen bonding description. What happens if we subtract this average spectrum? So we get just all these principal components are shifted to one place to the right. So here you get this second principal, your third is here, and your fourth, you're getting an extra principal component. What happens in terms of variance distribution? Still, you have 95. Okay, you're getting a little bit better distribution of variance, and still, this is very low. Okay, when you finally use the optimized subtraction of pure water with using the database, you get significant decrease. So from 98, is almost 100, you get to 70. And then your second principal component jumps to 20. And then your third jumps to 2.5. So these are still low, but they're almost 10 times, 20 times bigger than what you had before. So the distribution of variance changes. Your bands are filtered, your bands are visible now, and the principal components, so now you can think about what's happening here and so you get extraction completely. So this is where you were with raw spectra in the fourth principal component with 0.01 variance, and you got that up to 70% in the first principal component. Okay, so that's basically the end. I hope I left enough time for you to ask some questions, and this is the slide that I always want to like finishing with. This is a slide given. This is a paper from Forever Excellent Martin Chaplin. This is water's hydrogen bonds, and this is available for free online for an archive. You can have a look, and this is the table that is trying to remind us why is it important to have a precise measurement of hydrogen bonds. Because if you see here, this is if there was no change. This is the left column. This column shows the percent change in hydrogen bond strength. So 0 has no change. But these are the effects compared to 37, which is a biologically human body, right? That's the biological range. But it happens if it goes -2%, +2%. So you have significant metabolic effects, and things really, really go dramatic. As you continue shifting, each percent is presenting more challenge to life itself. So thank you for your attention, and I hope you enjoyed the talk. So I'm ready to take your questions. Thank you.
Thank you, Dr. Dusan Kojic. So now open for discussion.
It's behind you.
So thank you for the interesting talk. Just a question related to the last slide you were shown. What about the effect on the scores? Because from my point of view, should be very interesting to see the type of normalization, which type of effect have on the scores also.
Absolutely agree. That's my error. So I will take that into consideration in future. I will show the scores too. Thank you.
Thank you, Dusan. My question is, you mentioned that considerable collection of spectra is required as a background database. So what is your feeling how tall or how wide this pool of reference spectra has to be for the method to be effective and generally applicable?
Thank you so much for that question. That's something I'm thinking about recently. So the database that we had when the paper was published had about 11,000 spectra. Now that I mastered, when I can take spectra better, I'm down to 2,000 spectra. So, and the first, that was 11,000 spectra taken over a couple of years. But I didn't do any collection. I just gathered what I already had. And that database was not good. It had a lot of spectra, but most of them were focused around room temperature plus or minus 1 degree. So I was pretty vacant around a little bit outside of that, but now I'm happy to share that. It's a really, my technique is now taking just a few hours and you can take 10 times better, like 5 times less spectra. However, what you said is, can we go less than that? Can we take a little more work? So my idea currently is to take even less spectra, maybe just take spectra at each degree, or 2 or 5 or 10 degrees. The bigger gap, the better, and then use linear combinations. That would be the best. Or some kind of model to even predict.
You would extrapolate between the temperature steps?
Yes. Yes. So the question is, there is a trade-off, definitely. Because if that was possible, 100%, then somebody would have already made the temperature calibration that works, and then this would have already been known. I would have been behind the time. But for some reason, and there is a PhD thesis in the references that I'm supplying that made an excellent account of that data. The guy used linear methods, non-linear methods, all these things to build a model that you can use. And it's always, if you want to make a model practically useful, it has to have, the number of principal components just skyrockets. So it's unstable. So there is a trade-off in my experience. There is a trade-off between having real spectra, and now it's, I think, a couple of hours anybody can do. If you do, I'll explain. I mean, it just, you heat the spectra and you just let them cool. You just keep taking consecutives after the other. And by the time the sample is cooling, it's slowly cooling or heating, or it's equilibrating, and it's generating enough spectra. So that way you need like 2 hours to get an excellent database that you don't have to fit or anything. But I'm still very tempted, and I'm intrigued by your idea, by somehow using less spectra and extrapolating and then building it into a model. Maybe something better will happen. So I don't know. The short answer is no, but I'm trying to work in that direction.
Or maybe the optimum is somewhere in the middle. You acquire a certain amount of spectra, then you have a robust base to do the interpolation, and then you have the optimum of work and efficiency.
Just to find what is the sweetest spot in that, but yeah, those are the extremes. Thank you.
Any other question?
So I have no question, but I just to say thank you for your mission to our work. So one is the wavelet transform, to calculate the derivative computation. Wavelet transform to calculate the derivative is a very good method. So we published the paper maybe 20 years ago.
Oh.
So now in our work, so we always use wavelet transform to calculate the derivative. It get the derivative, and at the same time we can get a very smooth result. So it's a good idea to calculate. The second work you mentioned is our work published in Atlanta in 2010 to correct the temperature effect.
That's your work?
Oh, yeah, yes.
Okay.
That's my first work about the temperature effect.
Thank you.
So I will talk about this topic tomorrow. Okay.
Okay. Can I be in? Yeah, please.
Thank you.
No, thank you.
Just a note. There are temperatures, there are two temperatures that are causing non-linearities. So you have to be careful. 25, 30, 35. Strange temperatures. So bear in mind.
Okay. Yes.
Hello. Thank you very much for your presentation. I'm really looking for trying this out. I also tried out something that I read in a paper of Gowen, what's her name? Eva Gowen, and she used EMSC, and then she said use the first regression factor of the first PC to correct for temperature in your data set. Now, what is your opinion on that?
I haven't tried it, so my opinion will be very limited, but I had a PhD student who was trying to get that. He didn't finish the work, but the results were really encouraging what he was getting out of that model.
Yeah, okay, so,
Yeah, so
let's keep it that way.
Yes, 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 thank you.
Any other question? Comment? So thank you again.
Just one comment.
Yeah.
Thank you, Dusan. I really, really appreciate it. It's lots of work. But what I was listening to you, and I was thinking that this is good to compensate, but it is also good to use those variations as a source of information.
That's an advanced, I hope it will happen in the next. So my idea right now is to have, after subtraction, I would like to keep that spectrum of pure water that was subtracted. And that way, that's why you usually always some pre-processing, some information is lost, and there is always that doubt hanging in the background. Have I done something except for doing wrong? Have I lost something? So keeping those three spectra is actually the way to go in future to increase even more, because there is a mixed, I mentioned, there is a mixed effect, temperature shift and solute related shifts that are entangled. That at the moment I don't know how to untangle them, and as long as I am there, I will keep using the spectrum that was subtracted. So yeah, thank you.
Okay, so thanks again, Dr. Dusan Kojic. So before the next talk, I had an announcement about the participant. So pre-open lecture by Professor Lumian Tenkova was already finished. So if you want to join this symposium, you need a registration. If you don't finish the registration, please go to the registration desk. 日本語でもお伝えしましょうか。天小葉先生によるフリーレクチャーの方が終わりましたので、もしこの後続けて、このシンポジウムに参加する場合は、レジストレーションの方お願いします。